Dear students, Namaste everyone. In the previous classes, we studied normal distribution, especially the probability mass function of a normal distribution, the probability curve and the features of a normal curve. Those factors we studied. Now let us move to another distribution in this session. That is a chi-square distribution we have to study now. It is a continuous theoretical distribution, and the chi-square distribution is derived from normal distribution. So, chi-square distribution is derived from normal distribution. From which distribution chi-square distribution is derived? The answer is chi-square distribution is derived from normal distribution. Yes, sir. Next, the square of a standard normal variate is a chi-square variate with 1 degrees of freedom. With 1 degrees of freedom. The square of standard normal variate. We studied standard normal variate is denoted by the letter Z under normal distribution concepts. So, the square of standard normal variate is a chi-square variate with the 1 degrees of freedom. So, what is a chi-square variate? You must know the square of standard normal variate is a chi-square variate with the 1 degrees of freedom. That is, we can write like this. If X is a normal variate with the mean mu and standard deviation sigma, then we know Z equal to X minus mu by sigma is a standard normal variate with the parameters 0 and 1. You know this. This comes under a standard normal distribution, and Z square is equal to X minus mu by sigma whole square is a chi-square variate with the 1 degrees of freedom. This is a new factor now we have to study, and it says what is chi-square variate. Look at this, square of standard normal variate is a chi-square variate with the 1 degrees of freedom. Right? Now, here 1 mark question. What is the distribution of Z square? What is the distribution of Z square? The answer is the distribution of Z square is a chi-square distribution with the 1 degrees of freedom. Or we may ask like this, what is the distribution of square of a standard normal variate? Standard normal variate means Z. So, we can read like this, this square of a standard normal variate. So, what is Z square? That is the distribution of the square of a standard normal variate is a chi-square distribution with the 1 degrees of freedom. Right? Next, imagine there are 2 independent standard normal variates Z1 and Z2. What are those? Let Z1 and Z2 are 2 independent standard normal variates. Then Z1 square plus Z2 square, it follows chi-square with the 2 degrees of freedom. Once again, 1 mark question. If Z1 and Z2 are two independent standard normal variates, then what is the distribution of Z1 square plus Z2 square? That is a chi-square with the 2 degrees of freedom. Similarly, if Z1, Z2, so on Z8 are 8 independent standard normal variates, then the distribution of Z1 square plus Z2 square plus so on plus Zn square the distribution of this is a chi-square with the 8 degrees of freedom. Now see here, there are 8 independent standard normal variates. Then we have considered the square of the first sum of the squares of 8 independent standard normal variates. We have considered the distribution of this. That means the distribution of Z1 square plus Z2 square plus so on plus Z8 square is a chi-square distribution with the 8 degrees of freedom. Similarly, if Z1, Z2, so on Zn are n independent standard normal variates, then Z1 square plus Z2 square plus so on plus Zn square is a chi-square variate with the n degrees of freedom. N degrees of freedom. Or we can write Z1 square plus Z2 square plus so on plus Zn square follows chi-square with n degrees of freedom. The probability density function of a chi-square distribution is given by f of chi-square is equal to half power n by 2 divided by gamma n by 2 e power minus chi-square by 2 chi-square power n by 2 minus 1, where 0 less than or equal to chi-square less than infinity, n greater than 0. Right? Here in your textbook, instead of writing this probability density function, it is considered as f of chi-square is equal to k into e power minus chi-square by 2 chi-square power n by 2 minus 1, 0 less than or equal to chi-square less than infinity, n greater than 0, where k equal to half power n by 2 divided by gamma n by 2. Just this factor is replaced by k in your textbook. So while defining chi-square distribution, you can write like this: a continuous probability distribution, that is a continuous probability distribution which has the following probability density function: f of chi-square is equal to k into e power minus chi-square by 2 chi-square power n by 2 minus 1, where 0 less than or equal to chi-square less than infinity, n greater than 0 is considered as a chi-square distribution with the n degrees of freedom. And notationally we can write chi-square with the n degrees of freedom. Right? Here n is greater than 0. The parameter of chi-square distribution is n, where the parameter n indicate the degrees of freedom. Right? So here a chi-square distribution has a n degrees of freedom, which is also considered as the parameter of the distribution. What is the range of chi-square distribution? This is considered as a range of chi-square variate. The chi-square variate takes values in between 0 and infinity. It takes value 0 till infinity. Right? So, the first value of chi-square is 0 itself. See here, chi-square variate takes only non-negative values. Chi-square variate takes only non-negative values. It never takes negative values. It takes 0 till infinity. Okay. Here k is a positive constant depending on n. That is, as n goes on changing, the value of k is also changing. Right? So, a factor k, it is depending on n. So, it is given k is a positive constant depending on n. Now, we understood what is k and n as well as the range of chi-square distribution. Next, let us see the probability curve of a chi-square distribution, or that itself is called as a chi-square curve with the degrees of freedom n. Right? It is a xy plane. Consider chi-square variate along x-axis and probabilities along y-axis. Probabilities are given by the notation f of chi-square. And we know the probability, the total probability is always 1. Its probability never exceeds 1. It lies between 0 and 1. So, along y-axis we have to consider from 0 to 1. You will be getting here 0.5 and so on. Right? Next, here we have to write the values to chi-square. Chi-square, the range is from 0 to infinity. Right? So, here the first value of chi-square is 0. So, we can write here 2, 4 or 5, 10 and so on by fixing the scale. What is the probability curve of a chi-square distribution? These are different chi-square curves, right? And for that is for different values of n, that is the degrees of freedom, we will be getting different chi-square curves. Now, this first curve is corresponding to n is equal to 2, right? And next one is, here I am going to write 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 24, 26 and so on. Right? So, this curve is the chi-square curve with the 2 degrees of freedom. Next, here it may be n is equal to 5 or this may be n is equal to 6. And it may be corresponding to n is equal to 10 and this one maybe it is n is equal to 14. Simply I wrote the values of n, right? That is, what is this curve? It is a chi-square curve with the 14 degrees of freedom. It is a chi-square curve with the 10 degrees of freedom and so on. Now, just observe the chi-square curve for different degrees of freedom. When n is equal to 2, the shape of the chi-square distribution will be like this, and the chi-square distribution with the 5 degrees of freedom is this curve. Similarly, with the 10 degrees of freedom, this curve indicates the chi-square curve with the 10 degrees of freedom and so on. Now, first see the skewness of those curves. When n is equal to 5, 6, 10, 14 and so on, all the curves are positively skewed curves, because in each of these curves, the right tail of the curve is longer than the left tail of a curve. But we can compare the skewness of each curve. In the first curve corresponding to n is equal to 5, the difference between right tail and the left tail is higher when compared to the curve with the n is equal to 6. Right? Look at the difference between right tail and left tail of a curve with n is equal to 6 and n is equal to 5. Where the difference is more? The difference is more when n is equal to 5. Similarly, you can compare when n is equal to 5, n is equal to 6, n is equal to 10, n is equal to 14 and so on. Here we must note, as n goes on increasing, the skewness of the curve is also going on decreasing. Yet after reaching a certain value of n, we may observe chi-square distribution looks like a symmetric curve. Right? So as n goes on increasing, the degrees of freedom increases, the skewness becomes or approaches to 0. Similarly, look at the kurtosis, the peakedness of the curve. This is the peak point of the n is a curve with n is equal to 5. Right? So look at the peakedness of each curve. As n increases, as the degrees of freedom increases, the peakedness of the curve also decreases. That means here the chi-square curve is basically it is a leptokurtic curve, but as degrees of freedom increases, it reaches to mesokurtic curve. Right? That is, the peakedness is goes on decreasing as n tends to infinity. This is about a chi-square distribution, probability curve of a chi-square distribution. So here this is a chi-square probability curve. Let us study the features of chi-square distribution. First feature is, chi-square distribution has a single parameter n, which indicates the degrees of freedom. N is the parameter of chi-square distribution which indicates the degrees of freedom. Now what is degrees of freedom? Degrees of freedom is the number of independent variable components a distribution has. Right? That is, if any dependent variable values are there, those must be deducted from total number of variable values. Next, second feature, the range of chi-square distribution or chi-square variate is 0 less than or equal to chi-square less than infinity. Don't write here equal sign, only less than you have to write. Next, third one, it is a leptokurtic curve. It is a leptokurtic, that is a highly peaked. That is, the value of beta 2 is greater than 3. Similarly, it is a positively skewed. That is, the value of beta 1 is greater than 0. It is a positively skewed, that is, the beta 1 is greater than 0. Next, the mean of a chi-square distribution is n. Variance is 2n and standard deviation is square root of 2n. Next, the area under the chi-square curve. The area under the chi-square curve is 1. Like normal distribution or standard normal distribution, here also the area under the chi-square curve is 1. Next, what is the mode of chi-square distribution? Here mode is given by n minus 2 for n greater than 2 and it is 0 for n less than or equal to 2. You can observe this in the curve. When n is equal to 2 or less than 2, now here n is equal to 2, look at this curve. Only this curve we must observe. Here the peak point is this, the peak of the curve, and this is corresponding to y square equal to 0. And we know mode is the highest probability, right? The value corresponding to the highest probability. Here mode equal to 0 therefore. So n equal to 2 or when n is less than 2, mode is 0 in a chi-square distribution. If n is greater than 2, that means if n is equal to 3, 4, 5, maybe 20, 25, 30, then always mode is calculated by the formula n minus 2. So when n is equal to 5, the mode is 3. Yes, when n is equal to 10, n minus 2, 8, the mode is 8. So on. So in a chi-square distribution, mode is given by the formula n minus 2 for n is greater than 2 and 0 for n is less than or equal to 2. Similarly, one more feature, that is as n tends to infinity, chi-square curve or chi-square distribution tends to standard normal distribution, or skewness approaches to a value 0, coefficient of skewness, right? We can say as n tends to infinity, chi-square distribution tends to standard normal distribution. These are the features of chi-square distribution. Next, what is the use of or applications of chi-square distribution? Chi-square distributions are highly useful in the field of testing of hypothesis. Hypothesis means a statistical statement regarding the population. Here mainly chi-square distribution is used in 3 cases. The first one, to test whether the population has the given variance. That is to test the statistical statement regarding the variance of the population. That is the first use. And similarly, think of binomial fitting and Poisson fitting. For the given problems, we have fitted binomial distribution as well as Poisson distributions. In those cases, to test whether the theoretical distribution fitted to the observed data, is it suitable or not? To test that, once again chi-square test is used. So we can write like this: chi-square test is used to test whether the theoretical distribution is a good fit to the observed frequency distribution. And one more, it is used to test whether the 2 attributes are independent or not. So consider any 2 attributes. To test whether those 2 attributes are independent or not, chi-square distribution is used, right? And all those testing procedures comes under the chapter testing of a hypothesis, right? Let us solve some problems on chi-square distribution in the next session.